Hello everyone, thank you for joining us today for our Combined Remedy series. Today we have manganese activated persulfate for the treatment of recalcitrant organics, development and commercialization with Mr. Bruce Marvin from Geosyntec Consultants as our guest speaker. I'm Liz Mueller, our marketing manager for Carus Corporation. And just a few housekeeping items before we get started. We have all attendees in listen-only mode to help cut down on any of the background noise. If you have any questions, we encourage you to enter those questions into the questions pane that we'll see an example here on the right-hand side of the screen. And we are recording today's presentation, so if you would like the recording or PDF, please get into contact with me, and then I will forward you on to Bruce. If you also want a PDF, you can contact Bruce directly. Here's a couple ways how to find us. So we have our Carus Corporation website, our sales and marketing email address that comes in, and then we can best direct you to the person to answer your questions. And then here's also my direct email address. We're active on our social media platforms. So we have LinkedIn, a YouTube channel, Facebook, and Twitter, where we'll commonly post any upcoming events, webinars, recordings of our webinars, product content, and upcoming trade shows where we're doing presentations as well. And if you're interested in, we have a few more in this webinar series, and then we will kick off the second half of the year with additional webinars. So if you're interested in finding any of that information and registering, you can go to our caruscorporation.com website, and from there you'll find under remediation webinars, you'll find both upcoming webinars, and you'll also find an option of viewing information of previously held webinars. And just here's a quick look of our Carus contact information. So for our US sales, we have Troy Leiser and Tim Colgan. Our European sales are managed by Lorenzo Sacchetti. And we have Louis Hernandez, who covers Canada, Mexico, and South America. So I know this is just a quick snapshot of it. If you want to get into touch with them, feel free to directly reach out to me and I can put you in touch with those people. And at this time, I would like to take the opportunity to introduce our speaker, Mr. Bruce Marvin. Bruce Marvin is a senior principal environmental engineer based in California with more than 15 years of consulting experience focused on remediation strategy development, technology selection, engineering process design, and quality assurance procedures. His clients include private and governmental entities in the United States, Japan, Canada, and Australia. Bruce is internationally recognized for his in-situ remediation expertise, establishing industry best practices for ISCO, and performed numerous pioneering projects involving ozone, permanganate, and persulfate. Bruce received his BS in Civil Engineering from Northeastern University and his MS in Environmental Engineering and Science from Stanford University. He holds certificates in safety management through the American Society of Safety Engineers. We welcome Bruce.
Thank you, Liz. Good morning, everyone on the West Coast. Good morning, afternoon, everybody on the East Coast. My name is Bruce Marvin. I'm with Geosyntec Consultants in Oakland, California. And what I'm going to talk about today is kind of about a 5 or 6 year applied research and development project that I've worked on with my old friends at Carus Chemical. Carus has been an extremely supportive firm to the development of ISCO technology. Back in the late 90s, when we were first working with this funny thing called permanganate, Carus was extremely proactive in sharing chemistry information, engineering information, and commercialization support for ISCO as a technology, and their commitment has continued through this time. Pamela, who is one of my co-authors on this talk, has collaborated with me and Dr. Michelle Karimi on this topic for about 5 or 6 years, but we go back to when both Pamela and Michelle were PhD candidates and working with permanganate. And what we're trying to do here is see if there's a way that we can combine permanganate and persulfate in a single injected solution for the purpose of creating a more sustained ISCO chemistry. There's been a lot of work in the last few years on improving ISCO products. And really that's been coming out of the commercial sector rather than coming out of like a CERDIP or an ESTCP research sector. And I've listed here a number of different products. Calcium peroxide and persulfate, Closure CR, is one of my favorite combined remedies for hydrocarbon sites. We use it a lot to do an initial ISCO, followed by an aerobic bio, followed by an anaerobic bio. And then you have these other trade terms where basically persulfate and activators are combined into a single product that can be delivered to a site, readily mixed and delivered. So we're looking at trying to do the same thing, but with a slightly different activator system. As you can see above, calcium peroxide, basic silica, ferric iron, and then of course base are your classic activators for persulfate. But what we're trying to do here is use sodium permanganate and sodium persulfate together, which for the moment we're terming manganese activated persulfate, but also likely has a little bit of influence on organic activation of persulfate. And so that's what we're going to talk about in this talk, is the first half really about what is the basis and the theory behind this dual activator system and dual oxidant system. And then in the middle, we'll talk about a field site where we've done about 4 years of work in the field with this chemistry. Then we'll come back to a little bit of work on emerging contaminants, looking at other compounds to try to help us understand, are we having a direct oxidation process, or are we really having an advanced oxidation process, which an advanced oxidation process would be a persulfate activated system where we use a chemistry to initiate the sodium persulfate decomposition, and then a series of chain reactions occur that create oxidizing and reducing species that together I refer to as advanced oxidation, much in the same way you conceptually look at advanced oxidation in atmospheric chemistry. And delivery strategies here at the bottom, we just don't have time for today, so we'll have to save that for another day. So again, here's the outline of the presentation. I'm going to talk first about the background in the literature, largely focusing on how we came to this idea that we could use manganese as an activator for persulfate, then go through some results of field work where we started in the laboratory with our client support and Geosyntec support on doing some additional R&D outside of what would normally been a standard permanganate treatability study, and then talk about a little bit about recalcitrant contaminants, that includes the SR cylinder delivery technology from Carus, and some early field site work that we have for a TCE 1,4-dioxane mixture. So why? Why do you want to combine permanganate and persulfate? Well, the thing I like about permanganate is it's simple to inject. You have a single solution, you inject it simply, and the challenge with persulfate is often to get the activator chemistry right. It's not so much for persulfate about getting the delivery of the persulfate. That's straightforward. The persulfate doesn't react very well under ambient conditions unless your site happens to be in a sweet spot for matrix activation. Permanganate's a little more expensive than persulfate on a mass basis and an electron equivalence basis. So we may have some cost advantages if we combine those two mixtures together. Number 3, high doses of permanganate produce manganese oxides that have been implicated, particularly for DNAPL pools, as creating a rind or a coating that may limit mass transfer or limit the process from proceeding the way we would like it to. And permanganate and persulfate also have unique decomposition kinetics. And later in the talk, I'll show you a couple of those slides. But basically, permanganate is known to have a 2-phase kinetic demand, a fast demand and a slow demand. Persulfate, on the other hand, without any activator, has a very slow kinetics. So can we basically superimpose those two kinetics and get a vigorous activation system with permanganate acting at early time and persulfate acting at middle to late time? So our hypothesis was, when we began this work, was really that mixed manganese oxides that we create fresh from decomposition in the subsurface and the low molecular weight organics that may be formed from the permanganate oxidation of soil organic matter can be formed in situ while we have persulfate in the system, activating the persulfate and sustaining the ISCO treatment for a longer period of time. So what is our conceptual model? So I described that a little bit before. It's really that the permanganate in this mixture rapidly can oxidize dissolved phase contaminants, especially chloroethanes like TCE, and clear some of that demand out of the aqueous phase to create a scenario where the persulfate can be used more efficiently. As we know, permanganate reacts with soil organic carbon, and what we have seen over the last 20 years is that we often detect low molecular weight organics like acetone and butanone in our 8260 for our permanganate only sites that for a while were a concern, is this a byproduct? But in fact, we're trying to leverage that byproduct to create an organic activator for persulfate. And then finally, does the synergy of permanganate and persulfate decomposition kinetics allow us to enhance mass transfer by suppressing the concentration in the aqueous phase, driving mass transfer off of solids, off of the organic carbon that we're slowly oxidizing with our permanganate, and sustain an oxidation process for longer than we would with some of the stronger activation chemistries like base activation, which often we are only able to sustain the real vigorous chemistry for weeks at a time without the risk of overdosing and changing the pH. So here we have a circumneutral process that has the ability to give us fast kinetics up front and sustained kinetics over the long term. So how did we come to this idea? Well, back in 2010, 2008 timeframe, Washington State University and later UC Berkeley were investigating what I like to call matrix activation. So many sites found that if they injected persulfate solution, some sites would activate automatically and other sites wouldn't. And so there's been a great deal of research to look into, do the contaminants do that activation? Do soil minerals do that activation? Or do other organic compounds do that activation? And what you see on this slide is I'd really like you to focus on the pyrolusite, which in this here is our manganese oxide form. So here you can see our ferrohydrite and geosite are all iron oxides, and then silica, which is the basis for one of the trade mixtures, doesn't activate the decomposition nearly as much as manganese dioxide. And then we move over to the right and you see that clays and general aquifer minerals also do not get the same level of activation that we see from pyrolusite. So that led us to think, hey, we know how to make manganese dioxide in the subsurface. We inject permanganate in the ground. We often observe during our process monitoring a front of manganese dioxide arrive at our monitoring wells before the permanganate does. And this research led us to believe that perhaps we could create man-made manganese dioxide. So in this case, we're looking at naturally occurring burnessite and pyrolusite, but can we make a man-made version of that? So the next question is, well, should these fresh anthropogenic activators have more or less activation than naturally occurring material? So we went to the literature and we looked at zero valent iron, and we at this reference, these two references talk about the passivation process as well as the reaction rates of zero valent iron at early time versus late time. Then you get into mixed iron and manganese oxides with Furman, Doe, and Joe, all looking essentially at naturally occurring aged manganese oxides. And then you've got Ahmed coming in later looking at subsurface minerals, again, trying to understand which type of manganese dioxide, which type of ferric oxide really drives the process. And what you can see over on the right in my graph here is this is a plot of diesel removal, and it looks at different mineral forms of iron and manganese dioxide in that system and what happens when you have persulfate and persulfate versus iron 2 in your system. And you can see again, the manganese dioxide suggests that even with pH low on sand and with or without iron 2, the manganese dioxide outperforms the iron oxides as an activator for persulfate as measured by the amount of diesel removed from the system. And these systems had very high concentrations of diesel in them, but it illustrates the point. So the next question is, well, is there any synergistic benefit? So what we know from Furman's work with matrix activation is that a lot of times after the persulfate decomposition, that first step is initiated, we create peroxymonosulfate. And peroxymonosulfate, we can buy in a drum, we can take to a site, and we can inject, and it has a very, very fast reaction rate. It would be very comparable to injecting high concentrations of hydrogen peroxide. So we believe it would be transport limited. But nonetheless, this peroxymonosulfate and potassium permanganate data, which was really being evaluated for an ex situ application, gives us some insight into what can happen. So some of these structures, the nanostructure of the amorphous manganese oxide seems to be important. So what conditions you have for pH and redox when your manganese dioxide is formed, what other solvents, solutes you may have in your system, can have an effect on whether or not this manganese dioxide driven activation of persulfate is fast much. But the key of this slide is we want to look over again at this graph. So on the left side, you can see the gray bar shows permanganate only, and the percent mineralization is of a dye that they used as a surrogate for contaminant. You can see the light blue is peroxymonosulfate only. And then what they did in gray is they added the gray bar and the blue bar together to stack them and say, well, if we did just permanganate, potassium permanganate and just peroxymonosulfate, would the sum of those parts equal 38% removal? But they observed 54%. So you can see in each of these different cases with different tracer compounds, phenol, hydroquinone, and 2 dye substrates, that actually the combined benefit of a permanganate persulfate or permanganate peroxymonosulfate system showed synergistic benefit. So that was encouraging to us as well to continue to try to understand how this process works. So here we've just tried to put together two reaction pathway diagrams to try to illustrate what we believe is happening. So up here in the top left, you start with your persulfate anion, and then this first step of activation or hydrolysis is really important because that's where we're splitting the persulfate anion in half, essentially creating peroxymonosulfate and driving the formation of sulfate radicals, hydroxyl radicals, some case hydrogen peroxide, and through into superoxide, hydroperoxone, and peroxymonosulfate as drivers for a manganese catalyzed system. So in this case, you could have iron acting as your activator to initiate that initial decomposition. In our case, we could have low molecular weight organics activating that initial decomposition, running quickly to peroxymonosulfate, which Furman assumed that this reaction kinetic was instantaneous and said that peroxymonosulfate was actually not relevant to really determining what this rate of oxidation was because it was so fast. So again, the key to this process is how do we unlock the oxidation potentials in the persulfate? And just checking time, bear with me, someone had sent me a message that knocked my timer off. And so what we see is really there's an initiation step, there's a propagation step, and that leads to contaminant destruction and ultimate mineralization. So this is an important part of the work that we didn't really comprehend 5-6 years ago. And there have been a lot of groups working in parallel on organic activation of sodium persulfate. Ocampo, you can see this reference here, did her dissertation at Washington State University in 2006. Brant Smith did his dissertation at Washington State as well in the early 2000s. And Brant really is a leader in this organic activation chemistry. So I stole his first slide from a talk that he gave at the Banff, Alberta conference, which interestingly enough, I gave this talk for the first time in Banff the next year and missed Brant by a year. And we're working in parallel on 2 different things. But I think that today, what we're seeing with permanganate and persulfate and sodium persulfate mixtures is really a hybrid of manganese dioxide-driven decomposition, which is a more sustained and a longer-term chemistry, and organic activation, which happens as a result of the permanganate byproducts at generally earlier time and just after when the permanganate has been consumed. And what Brant shows here on one of his slides within this excellent talk is this initiation step. So the organic molecules are thought to donate electron to persulfate. So really, the organics come in here, break the persulfate into 2 peroxymonosulfates, and then chain reactions run off from there and do the chemistry that we hope to do. Now, it is important to bear in mind that organic activation can have a scavenging effect. We also can have scavenging effects on the various radicals that are formed from other solutes. So it's really challenging to go from a lab scale on a general hypothetical, let's say with a synthetic groundwater, to a field scale. So all the data that we'll be looking at from here is now field data that really help us understand the site. So this is the first site that we did the permanganate persulfate combination at Geosyntec in the field. We evaluated traditional ISCO, and then we did the manganese activated persulfate work on the side with financial support from Geosyntec San Francisco operations to pay for that, with our client support for letting us evaluate a new chemistry really is one of the biggest DNAP source zones in Northern California. So we still have 300 to 3 milligrams per liter of TCE in this source zone. It was subjected to pump and treat for 25 years, slurry walled off and isolated from the greater plume around it. The greater plume is on the order of a mile wide and several miles long with numerous source zones. But this location really was the central distribution facility for TCE for that whole mega plume. And so that's what we're going to be looking at. Here's some of our first bench scale test work, and I'll take you through this pretty slowly. So you got TCE in your biggest bar here. We have cis DCE, which is formed as a byproduct. We then don't see much vinyl chloride at all at this site. We see Freon 113, which is not a risk driver contaminant for us, but is nonetheless important as a metric, and also important for us to understand what the mechanism of the persulfate activation that we're achieving. So our control systems are sodium permanganate only systems. Iron EDTA didn't perform as well as permanganate alone. And then we start rolling into combinations, and these are mass ratios. 75% sodium permanganate or sodium persulfate to 25% sodium permanganate in a single combined injection. Here we have a delayed spike where we added the persulfate first and the permanganate later, and other combinations. And you can see here that really, with respect to TCE, may or may not be very compelling. But we did see complete cis DC removal and some interesting changes in the Freon that really suggest that we may have more of a direct oxidation pathway during this phase of lab work. Then we went into a second and third phase of lab work, which I don't really have time to show you all the details, but we looked at the speciation of the natural iron and manganese beforehand in the solid phase. We think understanding the iron oxides and manganese oxide in your solid phase when you start, understanding your total organic carbon and your potential to generate organic compounds from your organic carbon content from the permanganate is also an important site screening process. And in the second and third phase, we also looked more again at the questions of simultaneous addition, delayed addition, and pH adjustment. And we ran that for over 30 days. And that led to our design for the field scale. So what you're looking at here on the right is our field site. The darker pink areas are TCE concentrations that are greater than 10 milligrams per liter. And the pink line is a 1 milligram per liter TCE contour. And really what our objective here was to support site redevelopment. So this site was being redeveloped. The slurry wall that's here on the perimeter was installed in 1995. The area was subjected to pump and treat for the purpose of lowering the water table and creating an inward and upward gradient. And that achieved about 155 pounds per year of TCE mass removal. And so when this area was going to be completely redeveloped, we took a hard look at it and said, what are the maintenance costs for pump and treat? And what are the costs for doing an extended ISCO program? And can we save our client money by shifting our remedy to ISCO, reducing the price, and enhancing the mass removal? So in 2015, we began to work on this pilot study under EPA oversight. You can see here is our summary of our injection events. So our first injection event was 83,400 gallons in February 2015. And over on the right, you can see the ratio of the pounds of oxidant applied within those volumes. And what happened during our first one is we went out with the idea, we like to do large scale first injection events, or let me just say, I like to do large scale first injection events for ISCO these days to try to understand how I can use the ISCO performance monitoring data, the persulfate and the permanganate concentrations over time, the arrival at the site, and then the consumption as an active diagnostic to help me design what my second and third injection events may look like and really suss out where the residual mass is. So we started with a big opening shot and actually had some issues with treated water escaping the slurry wall. And what we think happened was we raised the water level elevation enough around the slurry wall to an elevation that had been dry since the slurry wall was installed, and a little bit of treated water got out. So we had to tail back our injection in November 2015. And so that 4,000 gallon injection later, I don't even talk about because I don't think it was really that meaningful for ISCO, but it really was a tuning of our hydraulics and our injection rates to address what was a concern about a loss of control of the treated injected fluid solution. And then back in January in 2017, we started back on the same track. And now we have 2 injection events planned for 2018. And we haven't decided what the ratio of the permanganate to the persulfate will be this year, because we have to bear in mind, in 2015 and 2016, we've been adding manganese dioxide to the system. So there may conceptually be a time when you want to turn down the permanganate if you have enough. But on the other hand, if your manganese dioxides are aged in the environment and passivated, you may need to add more permanganate at the end to continue to enhance the freshly precipitated MO2 activation. So anyway, data. Here's data for TCE. Our macro conclusion was in our first year, we had an equivalent mass removal to 25 years of pump and treat. So 25 by 155 was our calculated mass removal, largely driven by some of these dark blue bars. Here's our baseline at 310, 70, and 38. And then you see these other stippled marks. This is February 2015. This is May 2015, August 2015, December 2015. So because our dose was lower than we applied, we expected to see pretty strong rebound. And we saw some rebound here and here, but not as much as you might see. And down here, where our injection volume was limited, we saw classic rebound, which was then abated to some degree by the subsequent injection. So in 2015, we reduced our injection rates. 2016, we increased the volume back up. So we will extend these graphs out and keep looking at it. Here you got it on a linear scale. You can see what happened, but really these 3 locations drove our mass removal in that first year. So to give you some context, first we looked at after we looked at the TCE, we looked at the oxidant delivery and longevity. So one of the challenges with this chemistry is the permanganate imparts a purple color to the fluid, and so you can't easily do a field screening for both permanganate concentration and persulfate concentration. So we made the decision that we would monitor the permanganate in the field with a spectrophotometer until the visible color permanganate was no longer present, and then we would measure with wet chem the persulfate concentration. So Carus has, in the interim, come up with an analytical method in the laboratory that allows them to quantify both permanganate and persulfate at the same time in the solution. So if we want to do bench scale testing, Pamela can help us with providing better data than I have here on the permanganate and persulfate concentrations simultaneously. But what we observed during this first injection, so our large injection event, 13 days in duration, was about, at the end of our injection event, we had between 55 and 75% of our permanganate initial concentration in our process monitoring wells. We then observed a 2-day to 4-day half-life, and found that the permanganate persisted for about 10 to 30 days. So in our location with 300 ppm of TCE, we had about 10 days of permanganate longevity, versus at our locations that had an order of magnitude or two less TCE, we had longer permanganate longevity. And then by comparison, by the time the permanganate had run out at a location, at our high concentration location, we only had 10% of the injected concentration of persulfate, whereas other locations we had as much as 95. And I think what this really illustrates is that our chemistry is working the way we intended to, which is that we're using the permanganate for the fast oxidation, the fast chemistry, and to drive desorption and mass transfer off of the solid phase into solution where we have residual persulfate that is being activated by the byproducts of the permanganate oxidation process. Now we compare that to our third injection event, and I'm skipping the second injection event because I feel that the volume was really relatively irrelevant to ISCO. So we move to our third injection event, and we see that we get permanganate breakthrough faster than we did the first time. And then we beginning to see persulfate residual change in the different geologic media. So the shallower layer has lower concentrations of TCE, and we're getting longer sustained persulfate residual in that location, whereas the deeper elevations are having faster persulfate decomposition and consumption. So our system is behaving consistently with our conceptual site model. And then we move to the fourth injection event. We've now optimized our injection volume. We're able to inject in a shorter period of time, a higher volume, a higher dose, and we see breakthrough of permanganate faster. And after this fourth injection event, we monitored after 4 months, and we had persulfate residual in every location. And then we've gone and done some periodic testing, and we've seen residual for 6 months thus far. But we're not drawing any conclusions about our TCE data yet, because we generally wait for our permanganate and our persulfate to be completely consumed and allow some time for rebound, and then do an assessment of the overall efficacy. So now I'm going to shift. Now we talked a little bit about the background, then we talked about MEW, which is our biggest and longest field site. Now I'm going to talk a little bit about other contaminants, our collaboration with Carus and Clarkson, and touch very briefly on our collaboration with UC Berkeley. So Carus Corporation Sustained Release Technology. This is a paraffin wax carrier that's embedded with permanganate or persulfate, and then installed into wells and used as a long-term source of oxidant. When you look at these two oxidants side by side, we're trying to ask ourselves the question, is there synergy? Is there a benefit? And the curve on the left shows a standard permanganate decomposition rate. And these are column tests with permanganate concentration in the effluent shown here on the x-axis, and days shown on the y with a year about here, and different diameters or different essentially concentrations or different surface areas of permanganate to be exposed. And we see classic permanganate fast kinetics, breakpoint, slow kinetics. And then we compare that to persulfate. And when Pamela did her column tests with persulfate, she found that there's a lag time from these cylinders until the persulfate concentration coming out of the cylinders really peaks. And so when we started talking about what our observations have been and our interest in combining these oxidants, we said, well, what if we overlay these two on top of each other? Then we're going to get two modes of strong oxidation chemistry and a very long sustained tail. So that's what we believe we saw in it. So if you look on the left here, this is BTEX results. So we're kind of trialing here. Do we see benzene treatment? Do we see toluene treatment? Do we see ethylbenzene treatment? And that's really summarized here in this second order rate constant table, where you can say we see that permanganate, as we all know, doesn't react well with permanganate. It'll react slowly with persulfate, but it's working better when it's a multioxidant. And we can see that same kind of carries through. Here is 1,1-dichloroethane oxidation over time, and similar kind of plot. The DCA removal that you hear on the bottom right as a percentage is the blue dot, and that maps to the second y-axis. And you can see at early time, very high 1,1 DCA removal that then begins to tail off over time, interestingly enough, as the concentrations of the oxidants increase. So we don't think that necessarily 1,1 DCA is a great target contaminant for this chemistry, but something is happening here at early time that we still don't understand. And so there is more work to be done with these combined oxidation, permanganate and persulfate mixtures, understanding how they work better and really trying to drill down into the mode of action more. However, you know, we are still pushing forward in the field. So this is a Geosyntec field site. And really the focus on this field site that we're interested in is what's the 1,4-dioxane behavior. This site also has TCE, and our application of ISCO at this site is really for a source zone treatment to reduce the mass flux from a former vapor degreaser source area into a plume that is outside of the building that has been subjected to pump and treat for 20 years. And what we're going to do is do ISCO in the source area, and then we're going to do biological treatment in the plume. And then at some point, there's a boundary when we're shifting from an ISCO remedy to a bio remedy. This site is a fractured rock site. It also has an extremely low oxidant demand, single gram per kilogram levels. So we see very strong oxidant residual. And what's the most important thing for you here is we see our control results here for 1,4-dioxane in our more permeable material. And we see 1,4-dioxane loss over 20 days. That's about 50%. So maybe we'd love to see it go quicker. But if we have a sustained chemistry that continues to push this process and sustain this process out beyond 20 days, we may very well have adequate kinetics to deal with the 1,4-dioxane. This second one here shows a second soil sample from that same site. And you can see that the rate of decomposition is faster here, although there is some loss of 1,4-dioxane in the control reactors that were not sterile. They were control in there. They were no treatment, not sterile control. And this gets me kind of to the end and the wrap up. And so what are the next steps for this chemistry? Geosyntec has 3 projects going on right now. The Colorado site that I talked about, we injected last fall through a series of slant wells. We've seen very strong oxidant residual. I've got calls saying, hey, are oxidants still here? Is this a problem? And the answer has been, no, it's great. We have over 6 months of longevity, so we have plenty of time for diffusion into the matrix, diffusion out of the matrix. We're taking a look at API sludge treatment. So a combined oxidative treatment as a pre-treatment for API sludge as an alternative to land farming. And a confidential site that's so confidential, I can't tell you anything else about it on this slide deck. And we're continuing to collaborate with Clarkson, Carus. Serum, our treatability lab partner, is working closely with Carus on methodology and to help Geosyntec professionals screen 3 or 4 more candidate sites. We're working with University of California, Berkeley, but that's really mainly on PFCs with a different persulfate activation chemistry that the modes of manganese oxidation or activation or manganese and iron oxide activation and organic activation are likely very strong players in this treatment. But I am not saying that this chemistry can treat PFCs and saying we're doing R&D on that. And then really up here, the ongoing questions are, you know, is there really a benefit of base addition? When we look at the organic activation literature, there was a lot of work done with organic activation at high pH, and a lot of those results showed the production of reducing species rather than oxidizing species. I think I'd like to leave the group with a thought that, you know, persulfate can be ISCO or it can be ISCR. We can create oxidative species driving hydroxyl radical production, sulfate radical production, or we can create reducing species like superoxide. So keeping those in mind are really important as you try to understand and screen your treatability test data. And I really want to advocate that, if you consider this technology, that it's really try to find a client that is willing to do significant bench scale work, because there are things to be learned. We are still commercializing this technology. And, I don't think it's at a place where we can, hold our rule of thumb up and look to our bank of 50 sites. We have maybe 3 or 4 that can tell us how to design without a really extensive, almost more of a mixed design study than a contaminant kinetic design study. And with that, I will ask Liz to take it from here. Thank you.
Great. Thank you so much, Bruce. That was great. So we have a couple questions that are coming in. Just a reminder for anyone, if you hopped on a little bit late, please feel free, if you have questions now, to go ahead and put those in the questions pane. Also, here's Bruce's contact information, so you can definitely reach out to him. If after the webinar you haven't written this down and want to get into contact with him, let me know. I'll put you in touch with them. So one of the questions is, when selecting this approach for a site, what are your top selection criteria? Do you just look at the contaminant type, the concentration, location? Kind of a loaded question.
That's a good question. The first thing I look to is the contaminant mixture. Do I think we can treat that contaminant mixture? The second thing I look for is, where is that contaminant mixture, and can I come up with a delivery strategy that I think can overcome the geology or match with the site geology? And then I start getting into the next tier of really understanding the redox potential of the system and trying to understand the solid phase. We're often limited in this field by not having a lot of information about the organic carbon. Just the bulk TOC doesn't tell us much. We might want to understand the nature of that TOC, how branched it is, how saturated it is, what the different functional species on there. Those things will become important for this chemistry, as well as the iron content in the solid phase and the liquid phase, the manganese content in the solid phase and the liquid phase. So really understanding overall how those key parameters fit into your site would lead me to a decision on, is it a go or a no-go for this chemistry? Hopefully that answers your question.
Yep. And then another question is, was soil mixing alternative considered for the first site? How do you think the cost would compare?
At our first site, we considered lots of things. On a big surplus like that, often we have non-technical drivers. We didn't really consider soil mixing because the site had a building on it and then was going to be demolished and turned into a parking garage. And so we didn't feel that we could disrupt the geotechnical conditions at that site with soil mixing and use that approach. As well as we were given the challenge by our customer to say, we have a certain price that we've been paying for 25 years to do pump and treat within this slurry wall. What can you do within that price that's better than pump and treat? And so we considered bio, we considered ISCO, we considered breaching the slurry wall, putting in ZVI barriers, lots of different things. And when all of those, technical and non-technical factors came together, we arrived at the ISCO program I described.
Okay. And hang in there, Bruce. There are questions coming in. One more.
I can talk all day if you guys stay online.
One more is compatibility issues. Do you see any?
I think this mixture is actually somewhat favorable for compatibility because really, we're working at a circumneutral pH. So for the permanganate and the persulfate, we, don't require special equipment. We've had, Vironics inject this material before. We've had Greg Drilling inject this material before. No special injection material compatibility issues. And I think that what we're seeing is, with this chemistry, we don't see as much acid production as we do with an iron-activated persulfate or a matrix-activated system. Part of my theory on that is that we might be seeing sulfate precipitation that reduces the apparent acidity, but end of the day is I think that this is a relatively benign mixture with respect to material compatibility as compared to other persulfate activation schemes.
Okay, one more is, did you look at sodium versus potassium for both permanganate and then sodium versus potassium for persulfate?
We did not.
Okay.
We did not. That's an excellent question, and I think I'd be happy to collaborate with anyone on answering that quantitatively.
Okay. The ratios of permanganate to persulfate are site-specific and determined by bench scale testing. Is that inaccurate?
Yeah, I think that's a pretty accurate statement. You can start with the premise of which one costs more by the pound, and you probably would come to the conclusion that you should start optimizing on the persulfate the permanganate concentration or the sodium permanganate cost as a result. And because I'm a civil engineer, I looked at it on an integer basis first and said 1-to-1, 2-to-1, 3-to-1, 4-to-1. But I do think that the more that we work with this, and as we get new sites, we need to keep in mind that that should be an important goal of treatability testing, because the MEW site that we looked at is a coastal fluvial deposit that has high organic carbon content, high naturally occurring iron. And now we're out in Colorado in fractured rock where we have high iron and high manganese, but an extremely oxidized system that has very little organic carbon. So I expect those sites to act very differently, especially as it relates to the organic activation portion of the chemistry.
Okay. In the discussion of the matrix activation, what was included under the category of aquifer materials?
I think that's basically just saying that there's soil solids in those systems, I think. And I do think that that's where that research started, was let's look at a body of sites and see if sites activate soil differently and then try to understand why. But I think that that's what they're really focusing on, is it's not really the aqueous phase that drives matrix activation, it's the solid phase.
Okay. One concern with permanganate injection is aquifer fouling due to the generation of the manganese dioxide. Does the combination of the oxidants alleviate the potential of the generation of the manganese dioxide left?
Yes. So in short, we're injecting on average 25% of the amount of permanganate that you would be injecting at a straight permanganate site. However, I do feel compelled to say that, for many years I was skeptical of this idea that manganese dioxide can, create rinds or plug the formation. I think, I have been convinced that if you have a free phase DNAPL site with a pool and you inject enough permanganate, you certainly can create a crust or a coating on it. But I would encourage the practitioner to consider the volume of the aquifer that they're dealing with and the density and and as a result, the volume of manganese dioxide. And you may find that the manganese dioxide that you inject is trivial in the grand scheme of the total volume of the voids in the aquifer.
Okay. All right, it looks like we're getting through all the questions. So again, if you think of anything after, please reach out to us and I'll scan through. We receive a report where it shows the questions asked, so I'll be sure to scan through all those to make sure we didn't miss anything and get in touch with Bruce if we did. And we want to thank you again, Bruce. This has been great.
Yes, thank you very much to Carus Chemical for having me present this webinar and for providing me with technical information for the last 25 years. And thank you to PeroxyChem. They provide excellent technical support, and I'd highly recommend that people also talk to Brant at PeroxyChem. He can help you really get your understanding of the chemistry of the place it needs to be an effective ISCO designer. Thank you, Liz. Have a nice day.
Thank you. Thanks, everybody.